Yeah, now I hope so. We should start the session. Now I would request Professor P.K. Shah to introduce our distinguished guest, Dr. Shailendra Kumar Dwivedi sir.
Good afternoon, sir. Very warm welcome to Dr. Shailendra Kumar, sir. He will deliver a session on multi-mode features on PV-based microgrid with islanding, synchronization under grid outage. Dr. Shailendra Kumar, senior member of IEEE, has received the BTech degree in electrical and electronics engineering from Uttar Pradesh Technical University, Lucknow, India in 2010 and MTech degree in power electronics, electrical machines and drives from the Indian Institute of Technology, Delhi, India in 2015 and the PhD degree in electrical engineering from the Indian Institute of Technology, Delhi uh, in May 2019. He is currently working as an assistant professor with Maulana Azad National Institute of Technology, Bhopal. His research interests include power quality, grid integration, custom power device, microgrid and renewable energy, etc. Dr. Shailendra Kumar is recipient of prestigious POSOCO Power System Award in master as well as in doctoral uh, during doctoral degree in 2016 and 2019. He is also a recipient of Professor Somnath Mahendra Student Travel Awards for the IEEE PDS 2018 conference and the IEEE UpCon Best Paper Award in 2016 and 2018. So once again, I am welcoming Dr. Shailendra Kumar and now I am handing over to him for this session. Thank you, sir. Thank you.
Thank you. Thank you, Prasanji, for nice introduction. And I would like to thank GC Bharuch as well as especially Astosh for inviting me to share my views on power quality and reliability issues for distributed energy generation in microgrids. So to continue this session, I'm going to share my PPT so that we can have. So this PPT is visible.
Yes, sir. Yes, sir. It is coming.
Okay. Yeah. So good afternoon, all of you, all the participants. And here for next couple of hours, we are going to discuss like multi-mod features of photovoltaic battery energy storage based microgrid with islanding synchronization under grid outage. So what we observe in an Indian grid scenario, I mean, if you talk about US or UK, so there is a well-established grid. So this system is developed or this microgrid has been developed by keeping in mind Indian grid scenario. So what we observe generally in Indian grid scenario, if you leave the, I mean, if you are not talking about the cities like Delhi or some other means well-established city, but if you are talking about the rural areas, so we are not getting the continuous power supply there. Okay, means for 6 to 7 hours there is a grid outage, and then we are facing the issues. So I mean there is interruption in the utility grid, and at that particular moment, if you are having a some emergency load kind of thing, like if you are having what we can say emergency load, suppose there is a hospital. So hospital cannot afford the loss of electricity. And you can assume if one doctor is doing some kind of surgery or operation, so and there is an interruption in the electricity. So what will happen? So by keeping these scenarios in mind, we have developed this particular system so that when there is islanding, this system can continuous the power across the load. Okay, this system can continuous supply the power across the emergency load. Okay, whenever grid appears or there is recovery from the utility grid, suppose there is any kind of fault and you have isolated your photovoltaic battery energy storage based microgrid from the utility. And as utility recovers, at that particular moment, you have again connected your photovoltaic battery energy storage based microgrid to the actual grid. What would be the advantage? We can sell the electricity if we are having a excess electricity apart from the battery energy storage. So some energy need to charge the battery whenever in a standalone mode, suppose PV is not there. So you have a battery energy storage and you have discharged this battery energy storage to feed the continuous power to the load. So you have discharged the battery at that moment. As grid recovers, so this PV energy, if sufficient and it is more than the battery energy storage and the load which is connected at the microgrid. And so these two components will consume the energy if battery associated is less than 80%. So we have to charge the battery as well as we have to supply continuous power to the load. So PV will supply these loads as well as battery energy storage, as well as charge the battery energy storage. If excess power still is there, then this excess power can be sent to the grid so that the consumer or the customer can earn the money at that particular moment. If you have generation more than the battery energy storage and more than the load demand. Why we are calling it as a multi-mode features? Why this microgrid has multi-mode features? So apart from energy management, apart from the energy distribution among the battery, load and the grid, this also addresses the power quality issues. Okay, power quality issues means suppose we are having a converter, voltage source converter. So in this particular system, the voltage source converter is the main device which convert this DC power, DC electricity, whatever you are having into the AC. Okay, so suppose we are having a conventional solar inverter and we are not taking any additional features from this particular voltage source converter. So this voltage source converter is used only for injection of active power. Okay, only PV array is available and this PV energy has been transferred to the AC and then injected to the grid. Okay, if load is not there, if you are talking about simple PV inverter or simple grid connected PV systems. But what is the issue? The utilization factor of this VSC is very poor. Utilization factor of this VSC is very poor. Even though we have a spare capacity of the converter. Spare capacity means up to 60% we are utilizing. Suppose you have taken a 5 kV inverter. So only 3 to 4 kilowatt power you are going to 3 kilowatt up to 3 kilowatt you are going to inject to the grid. So rest of the capacity we can utilize for other feature.
Sir,
other feature means.
Sorry to interrupt. Is the slide is moving, sir?
I'm still on first slide.
Okay. Okay. Thank you, sir. Okay. Yeah. Thank you.
So what we were discussing, that spare capacity of the inverter. So in these systems, the main concept is how you can utilize voltage source converter spare capacity. Okay, apart from active power injection. So in this particular topic or in this particular research area, you can, if you are having a photovoltaic and battery energy storage microgrid, you can divide into two parts. One is active power injection without spare capacity. One is active power injection with spare capacity. So suppose 60% active power you have been injected to the grid, 40% capacity is still available. So if you are using a solar inverter, this utilization factor of this inverter is poor. Even though nighttime you are not utilizing, nighttime photovoltaic energy is not there. So nighttime this you need to shut down this converter. However, in case of this system, the rest 40% spare capacity can be utilized for power quality improvement, harmonic mitigation, reactive power compensation, load balancing. There are n number of features. Voltage harmonic mitigations means voltage and current both are both harmonics can be mitigated using this voltage source converter. So n number of features. So if you are taking a load balancing, you have to see the converter rating. If you want to take the reactive power compensation, you have to again you check the converter rating. You cannot use same converter rating which has been utilized for a reactive compensation plus active power injection. If you want to add the additional features, you have to see the capacity of the inverter. If you have a spare capacity, you can utilize these voltage source converter in microgrid for n number of features you can do. You can take load balancing. Load balancing means, what does it mean? Load balancing means we are doing, there is some unbalancing from the load, but the grid currents are maintained. Grid currents are maintained. There is no balancing which appears across the grid current, even though your load is unbalanced. So these kind of features, multi features we have incorporated in these photovoltaic battery energy storage based microgrid. Apart from islanding synchronization when there is a grid outage. Grid outage means when there is outage of grid for 6 to 7 hour, grid is not there and then grid is appearing. So synchronization and islanding is also taken care in this particular system. So if you see the motivation and objective for this particular system. So recently, if we see the MNRE has taken several steps. Why they have taken several steps? Because you know the pollution level in India. AQI, people are always worry about AQI index, if I'm not wrong, air quality index. Okay. So to improve the air quality index in city like Delhi, there is abutment of diesel engine because they are polluting the environments. Suppose there is 100 houses and to interrupt and there is interruption in the electricity, so they have a backup through diesel engine. So what will happen? If 100 houses they have switched on their diesel engine, you can assume the pollution level in that particular area. So it is very dangerous for humankind. But what could be the solution if you are avoiding these diesel engines? And the another issue is related to diesel. This is the fossil fuel, and the cost of fossil fuel is increasing day by day. So to abutment of these diesel engine or to remove these diesel-based generators, an energy storage is required. So what we can put a 5 kilowatt rooftop PV along with this energy storage to avoid the outage of electricity. So whenever there is outage, you can switch on your PV or you can switch on your energy storage. If PV energy is not sufficiently available, suppose in evening time it is not available, so energy storage is there. You can use the energy storage to fulfill the demand. So the PV with battery and grid synchronization and desynchronization. Whenever there is outage, system can be desynchronized from the utility. Whenever there is recovery from the utility side, there is grid synchronization. So this system with these features is a good solution for a residential area. When I'm not talking about only urban area, this is very good solution for rural area also. Wherever we are having a residential area and we want to remove the outage of electricity. What are the problem in conventional solar inverters? What are the problem? What is the problem in conventional solar inverter? Grid connected conventional solar inverters. For protection regions, solar inverters are mandatory to shut down. The important aspect of solar inverter is grid tied solar inverter, I would say. There must be a grid. Without grid, we cannot operate this solar inverter. We can operate in standalone mode separately and in grid connected mode separately. But switching off standalone to grid connected and grid connected to standalone, it is not available in the solar inverter. Okay. So if grid is not there, why I'm saying this one? Because you can understood the concept. Let me legend. Yeah. If we are removing this grid or if there is loss of the grid, so what will happen? Can you think? Simple grid tied solar inverter is there. Let me draw in this so that we can understood. So suppose we are having this whiteboard is visible. Can someone confirm?
Yes, yes.
Okay.
It is visible, sir.
Yeah. So suppose we are having this PV array here, and you have, I'm simpling here, I'm drawing the block diagram. I'm not drawing the internal circuit. Internal circuit I'll show you. So some device DC-DC converter we are having for MPPT purpose. Okay, DC-DC converter for MPPT purpose. And then we are having DC link capacitor, and then we are having VSC, voltage source converter. Please mute yourself. So here voltage source converter is there. Then we are having a grid in solar inverter. Simple. I'm not going to take any load or any other filters or some other thing. So this is the, I mean, the block diagram which we have taken here. So what will happen? You have applied some, at this point of common coupling, you have applied some switches, relays, all those things here. So as there is fault toward the grid side, you have removed, or the circuit breaker, the relay has given the instruction to the circuit breaker, the grid will be open. Now, if this energy storage device, I would say this is the infinite energy storage. Grid is known as infinite storage. So if I'm going to remove this grid, what will happen to the rest of the system? Can anyone tell me? What will happen to the rest of the system? If you are not going to switch off the VSC, if you are not going to switch off the VSC, what will happen? Can you think? I want to keep the this particular lecture interactive, because this is the means after lunch it is very difficult to attend the lectures, even though it is also difficult to deliver. But here I want to make this class interactive or this lecture interactive, so that at least you can get something that in that particular STTP we have learned this thing. At least those people who are working in this area. Okay. So here, if I'm going to remove this grid, from the PV array side, it is always operating at MPPT. It is always operating at MPPT. But there is interruption in the flow of power. There is interruption in the flow of power. Means there is no way where this PV power will go. Because you have large storage here, but this large storage has been removed as we have fall toward the large storage. So if you have not given the off instruction to this VSC through your control, what will happen? What will happen if you are not given this instruction to off instruction to the VSC? All the power, because you are operating at MPPT. Remember, your control algorithm, we are pushing that this PV array, if you have designed a 50 kilowatt MPP power, it will give you the 50 kilowatt. MPP power, I'm saying MPP power. We are having an open circuit power. Open circuit power, you can see the curve like this. So here we are operating. Okay, initially we are sitting here, but as we are operating toward the MPPT, so here we are operating. So we are getting a, suppose we have designed a 50 kilowatt, 5 kilowatt, 10 kilowatt, whatever the PV rating is there, number of series and parallel modules will decide the rating of this PV array. So if you are having a 50 kilowatt, 5 kilowatt PV power, and it is operating, always operating at MPPT, as we have assumed, grid must be there. Grid must be there. But when fault occurs, Grid is not there. At least some protections you have to provide to this system. So protection is only you have to give the command to your controller so that the VSC can be switched off. If VSC is switched off, this boost converter parallelly will be switched off, and there is interruption in the power. So what will happen in that case when it is operating at MPPT? You might have seen we are having a reference DC link voltage, some value of actual DC link voltage, sense DC link voltage, and one is we are having reference DC bus voltage. Reference DC bus voltage. So at that moment, your control will fail when we are having excess power at the DC bus, and this voltage may raise from 700 if you are talking about a three phase 700 to 1200, 1500, or even though more than this value, even though more than this value. Therefore, and if you design this DC line capacitor, if you are taking a 700 volt, hardly we can take, we have to include the safety factor. So 25 to 30% we can include the safety factor. So actual voltage plus 25% of its rated voltage. But hardly it is 900 volt, 1000 volt or 1200 volt, not more than that. And if you are reaching from 700 to 1500 volt, because there is no power flow, there is no way to flow the power, and it has been interrupted in between. So this DC link voltage will increase to beyond its limit, and this capacitor may blast. It will result in blast of this capacitor. If you are not including this off instruction in your control so that the VSC can be tripped when grid is not there. So this kind of instruction means this kind of instruction we have to include in our control. Whenever grid is not there, this VSC must be switched off, and as well as your MPPT also switched off. So that's why we are saying here we have included from protection for protection regions, solar inverter are mandatory to shut down under.
Excuse me, sir. I have a. Sir, can you
Yes.
please go to that previous window?
Yeah, sure. Yes.
Sir, in this case, suppose if we consider load also.
Pradeep Raj, you can ask your query.
Yes, sir. Sir, you can explain the MPPT, which type of MPPT used in DC to DC converter? It is a buck boost converter or other?
No, here I told you we can use, there are isolated and non-isolated converters. So in isolated converters, there are flyback, SEPIC, JITA, there are multiple converters which are available. But mostly in case of this simple PV system, people are using boost converter. Okay, people are using boost converter.
Thank you so much, sir. Thank you so much.
Yes. Yeah, another question was there.
Yeah, sir. In the same situation, if we consider load also, so then what about the operation, sir? Because during this example, the load is not considered, no?
I hope this is not the right time to tell you the answer of this question. Can I answer this at the end? Because you will find this answer whenever I'll discuss again my PPT, because the same scenario, this is the scenario which we are having during the islanding. Suppose grid is not there and islanding, during islanding, what will happen? We have to provide the continuous power to the load. Okay, so these all the controls, what are the controls in which we are having the islanding and when we are having grid connect? So in that case, suppose load power you have taken, let me answer right now, and in coming slide you can understand the concept if you are able to understand right now. So I'm going to explain it. So suppose we have connected the load and there is grid outage. You have designed a 5 kilowatt PV. So 2 kilowatt load, suppose I'm going to put here. I'm going to put here, I have taken 5 kilowatt 2 kilowatt load we have put here. So what is the power which was going to the grid?
3 kilowatts.
3 kilowatt power will go to the grid. So apart from 2 kilowatt, 3 kilowatt will be stored in this capacitor. So what we have to do, even though this capacity is this 3 kilowatt is more than the capacity of this capacitor. In that case, we have to operate this particular MPPT in off MPPT mode. Off MPPT mode. So I have shown you the curve. Suppose this is the PPV and this is the VPV. And here I'm getting the 5 kilowatt. So in algorithm, what we have to do, we have to operate this particular point somewhere here or somewhere here or somewhere here as per the requirement. So that it can supply only 2 kilowatt in case of standalone mode. It can supply only 2 kilowatt to the load. And at that moment, we can operate that these are the points where I can get the 2 kilowatt. So in our algorithm, suppose I have used a pattern observer or INC based algorithm. In that algorithm, we have to use the condition of if and else. Grid is 1. We can go with the full rating. If grid is not there, grid suppose 1 and 0 we have taken for on and off. So if grid is not there, G is 0. So we can operate in off MPP mode. So this way we can operate this system in a standalone mode by operating your PV array in off MPPT mode. I hope I have given the answer of your question.
Yes, sir. Thank you, sir.
Yeah.
Yes.
So this way we can operate these systems, and the protection regions, due to protection regions, we have to go these solar inverter. I mean, we have to shut down these solar inverters at the loss of the utility grid. However, the feature which we have discussed right now, I mean, multitasking photovoltaic battery energy storage microgrid has been developed to establish mini grid to supply power to the consumer load even at loss of the grid. So we can operate this multitasking photovoltaic battery energy storage based microgrid in standalone mode, and we can continue supply power to the loads. The other features which by which we are saying this system, microgrid system, is a multi-mode feature based. So we are having photovoltaic battery energy storage based microgrid system, and extracted active power is shared between the load and the utility. Moreover, this microgrid can be operated under outage of PV source. First condition, in night time PV is not available. So this system has the capability to operate in without PV array as well as without utility grid. So second condition we have considered, there is no utility grid, which in turn increase the utilization factor of photovoltaic battery energy storage, and it decreases the payback period of power converter. I'll discuss this thing. Remember this particular point we will discuss in coming slide, how we are going to increase the utilization factor of power converter. Power converter means nothing, it is a voltage source converter. Okay, the voltage source converter which we have used for transferring of power, or which we have used for additional features. Okay, what are the other features? Reduction in the distribution losses, enhanced utilization of installed distribution equipment. We are having a bidirectional power flow, so in both the direction we can use these systems. Bidirectional power flow capability, import and export. The bidirectional power flow is possible in these systems. No need of bulky magnetic transformer. So here we are not using any kind of isolated converters for bidirectional battery charge and discharge. Here we are using a simple buck boost converter for battery charge and discharge, or bidirectional converter. Using static switches, we can improve the reliability of the system. Static switches means now slowly we are moving toward the topology of this photovoltaic battery energy storage based system. So after this point of common coupling, we have put some switches, power electronic switches. Static switches are nothing but power electronic switches. And so by having relay and circuit breaker, they are having their own response time. I mean, there is delay, they will take 1 to 2 seconds or more seconds to switch on and switch off to give the instruction. Here we are simply using the power electronic switches. They are having the response time in microseconds. They are having the response time in microseconds. So this way we can improve the reliability of the system. The other features, we have tested the system under point of common coupling voltage variation, this photovoltaic battery energy storage based microgrid, indirect cost reduction by reducing losses and minimizing tripping. Even though there is variation in the grid voltage, the system is not tripped. PV feed forward loop in current control mode so that the system response can be improved. So that the system response can be improved. This PV feed forward loop has been incorporated in the current control. How these microgrid system, solar PV based battery energy storage based microgrid system has been classified. So we are having a grid interactive PV base. So based on the supply phases, you are working on a single phase system or you are working on a 3-phase system. So based on the supply, they have categorized. Again, the single phase and 3-phase, single phase has been categorized as per the number of stages, as depending on the number of stages. Single stage and 2 stage. So what does it mean? Single stage and 2 stage? And which system is good? We are not talking about battery storage till now. We are only talking about the grid connected PV system, which is having single stage, and grid connected PV system, which is having 2 stages. What would be the advantage of single stage and 2 stage systems?
Complexity and losses, because one more converter will come in 2 stages, DC-DC converter along with.
Okay. Okay, so you are saying that 2-stage system is good. Sorry, single stage system is good.
When we consider losses and efficiency into account, then single stage is better. When the PV array available voltage is less, then the 2-stage is better.
PV array losses.
PV array voltage.
Okay, PV array voltage is less than
2-stage is better.
So again, I am going to modify your statement. Boost converter is not used to boost the voltage in grid connected PV system. Remember, boost converter is not used to boost the voltage in case of grid connected PV system. Why? Because boost converter has only 1 degree of freedom. Boost converter has only 1 degree of freedom. It can either boost the voltage or it can do the MPPT. It can do the MPPT or it can boost the voltage. So what purpose you have taken boost converter here?
Obviously for MPPTs.
Obviously for MPPT purpose. So we cannot boost the, I mean, not more than 20%. Up to 20% it is okay. But once you are going to boost, suppose your DC link requirement is 700 and you are saying I will put the panel, I put the number of modules in series so that I can get the PV array voltage 300 and I will boost from 300 to 700, which could not be possible. Which could not be possible. If you are doing so, there is huge losses in case of in boost converter itself. Therefore, the overall efficiency of this PV system will be decreased. So we are restricting. We have I mean, we did all the calculation, all the loss analysis at what would be the duty ratio? It is 20%, 10%. And if you are moving from 20% to 40%, so what would be the losses in that system? So we have did all the calculation. Like here, the purpose of boost converter is only for MPPT purpose. So we have to put sufficient number of panels, sufficient number of modules in series so that I mean the duty ratio could not be increased beyond 20%, beyond 0.2. Okay. So in single stage, what does it mean? We are having again PV array and we are not putting any kind of converter for MPPT purpose. So here VSC, this VSC will do both the functions. What are the function? First one, it will do the MPPT. This VSC will do the MPPT as well as it will used for DC to AC conversion. However, in case of two-stage system, you have boost converter. And then we are having a DC link capacitor. And then we are having this VSC. And then we are having this three-phase grid load, all those things. Here we are having a separate unit for MPPT and separate unit for DC to AC conversion, and then for I mean the multi-mode features like power quality improvement and other features we have taken care by this VSC, this DC to AC converter. Now again, I'm going to repeat my question. Which system is good? Or which system industry still they are following that system? I mean, from this single stage and two stage system, industry is following only one system. They are not going, I mean, for two stage or single stage. They are following only one. I mean, industry, they are making a solar inverter with single stage or two stage. These
two stages.
Yes. So these single stage, not, I mean, now they are preferring this two stage, but earlier they were having this single stage. I mean, it's still not all industry, few industry, they are having this two stage solar inverter, but earlier they are having a single stage solar inverter. The reason is same as you told, that this boost converter is having losses. We have to put the inductor. So inductor will also have some quality factor, as well as we are having one switching device, one switch and a diode. So losses will always be in the picture. But what is the advantage? What is the advantage of single stage system? First, let's see the advantages of single stage system. First, advantages of single stage system. So what would be the advantage? We don't have losses, so efficiency is good, as well as boost converter is not there. But what are the disadvantages? What are the disadvantages? How you will decide the DC bus voltage? Suppose we are having a 415 volt grid here. So according to power electronics calculation, we have to put this 700 volt. Isn't it? We have to put 700 volt. In single stage system, if PV array is not there, then this capacitor voltage, if PV array is not there, then this capacitor voltage is decided by the grid. Or if we are having a two-stage system, because there is decoupling between PV array and this DC bus capacitor. In between, we have connected one boost converter. So this PV array is decoupled from the DC bus. PV array is decoupled from the DC bus. So as per the grid voltage, we can select this 700. But in case of single stage, we cannot directly interlink the grid voltage with the DC link because this PV array is directly connected to the DC bus. DC bus means this capacitor. So what will happen? Whatever the modules which you have put in the picture, number of modules, series and parallel modules. Series will increase the voltage rating, parallel modules will increase the current rating of that particular module, that particular array, PV array. Okay, PV array. So as you increase the series rating, you have. So we are having open circuit and open circuit voltage, and another is MPP voltage. And always we have to operate at MPP voltage. So in MPP, again, I'm going to draw the curve. This is your open circuit voltage. And here when we are operating at maximum power, this is your MPP voltage. So there is difference between OC, open circuit voltage, and MPP. So suppose you have selected a 700 volt open circuit. So fill factor will come into the picture. Suppose the fill factor we have taken 85.85, 85%. So what would be the MPP voltage? MPP voltage will be 700 multiplied by 0.85. So how much you will get? 80 people are taking 80% or 85%. I mean, suppose 500 to 600 volt you will get. So when you are operating this PV array in case of single stage at MPP point, you will not get 700 volt. You will not get 700 volt. You will get somewhere 500 to 600 volt. So can you synchronize this much DC bus with the 415 volt grid if the DC link voltage requirement is 700? How you can synchronize your converter, your VSC with the grid having a DC bus of 500 to 600 only? You have to maintain the modulation index as well as you have to maintain the voltage ratio, DC bus and 415 volt grid voltage ratio. So sometimes what are the things which we have observed? There is tripping in the voltage source converter if you have not taken sufficient number of DC link voltage. So what would be the solution? If you want to raise the voltage from 500 to 700 in case of single stage, what is the solution? Suppose I want to raise the voltage from 500 to 700, this DC link voltage in case of single stage. What I have to do?
You can go for more number of panels in series.
Exactly. We have to increase the series number of panels. So the panel which we are using for two stages, in case of single stage, we have to use not 5 panels, only 1 yet or 2 panels we have to use more. Here we are making the calculation, but if you see the exact system, we have to put 1 or 2 panel extra in case of single stage. So that the voltage, this voltage can be raised to 750 volt or 800 volt. This PV voltage, VPV can be raised to 750. So whenever you have chosen a 750 here, whenever it will operate at MPP point, you will get 700 volt at MPP. Now you have to change the design of VSC. Change the design of VSC. So little I'm going to deep in the power electronics. Deep in the power electronics. Deep in the power electronics means we are having a IGBT switch. How the blocking voltage of this switch is decided? Electronics people can answer this question. How the blocking voltage of this switch is decided? Capability of blocking voltage. I mean, whenever this switch is off, it can sustain the voltage as per the DC bus. Okay, so whenever you are going to switch off the system, or whenever there is no I mean current from the PV array, but it is open circuit, so you will get the 750 volt as DC bus. So you have to design this switch as per 750 volt, or if you have taken a 800 volt. So you have to design your system, you have to design your switch as per 750 or 800 volt. And it will also include the safety margin. 25 to 30% safety margin we have to take. So for 750 or 800 volt, suppose we are taking a 1200 volt switch. For example, okay, 1200 volt switch we have put here. Or you can take, you can increase the safety margin. Fusee switch we are having, semicron based switch we are having, they are having a different safety margin depending on its capability. So in case of single stage, there are two things. We have to increase the number. So disadvantage I'm telling you, we have to put 2 to 3 extra panel in series so that we can achieve the desired DC bus voltage. Second observation is, first observation is this, because we will not get the sufficient DC bus voltage. Second observation is, as per DC bus voltage, we will design the switch. We will design the switch. So what we have to take? We have to take the switch of higher rating as compared to two-stage system. As compared to two-stage system. Now we'll look into the two-stage system. In case of two-stage system, you have decoupled this this solar PV array or PV array from the VSC with the boost converter. So even though you have selected a 700 volt here, it will go from 560 or 600. But here you have selected some duty ratio like 20%. So 20% is allowable limit by which we can boost. So it is reaching to suppose 550 or 600 volt. From 600 to 700 we can boost, or 650 if it is reaching. So 50 voltage, 70 voltage, 80 voltage we can boost so that we can reach to 700 volt. So here number of panel are same. Number of panel are same, but we have used a decoupling device. And your IGBT switch will also be designed for as per 700 volt. The blocking voltage of this inverter or this converter, DC to AC converter, will also be decided based on 700, not based on 750 or 800. So the problem of tripping can be avoided in two stages as well as, and remember, the losses in the boost converter can be minimized by putting these two terminal voltage, PV array voltage and DC link voltage equal. So there is no circulating current. If there is a voltage change, so circulating current will flow. So switching losses in that particular converter can be reduced. In that particular boost converter can be reduced. So this is the scenario for single stage system and two stage system, how we are going to deal with each system. So everyone knows, people are saying, yeah, this research is going on grid connected PV system from last 20 years. Nothing is remaining. But if you are able to develop a manuscript or paper, I would say some technical document, even though by comparing single stage and two stage system, if you go into the deep, you will find out n number of things, and people still they are publishing in these area. I mean, in this grid connected PV system. So n number of things are involved. If you are a power system guy, you can look into these system from a power system aspect. If you are a power electronics guy, you can select for like me. I'm a power electronics guy, so I'm looking this system through power electronics way. How we can improve the efficiency through power electronics only. Okay. So this way we are having these systems so we have categorized in two-part basic. And at the end of this discussion, again, if you'll ask which system is good, sir, according to you, I would say there is a trade-off between two. This is the trade-off between two systems, between single stage and two stage. So as per your requirement, you can use these systems. So single stage, further, these systems are categorized into battery-less, battery-based, two-stage, battery-less, battery-based again. Single stage, we cannot have directly, battery without control. However, in case of two-stage, it is further categorized battery without control and battery with bidirectional converter. Battery without control and battery with bidirectional converter. Why we are not having two-stage system without battery? Without control, sorry, not without battery. Two-stage system, here you can see that single stage system, it is categorized battery-based system. Single stage battery-based system is categorized only in one part. Battery with bidirectional converter. However, battery-based two-stage system has been categorized into two parts: battery with control and battery without battery with bidirectional converter. Because if you are putting the battery without control and your PV array is always operating at MPP, PV array is always operating at MPP. So all the power will be dumped in the battery, even though battery SOC is more than 80%. So it may blast if you are not having, because you don't have any kind of boost converter by which you can control your PV array in off MPP mode, I would say, in off MPP mode. So this way we cannot have this without control. We always require control with the battery. However, in case of two stage, you can mechanically switch on and switch off the battery and you can put this battery without control. However, we are having a facility like we can put the bidirectional converter to control these battery. Other side, if we see the three phase has been divided. Three phase solar PV based microgrid system has been divided into two parts. That is the three phase 3 wire and three phase 4 wire, depending on the number of wires. Why three phase 4 wire? Because neutral current compensation sometimes you require. Because sometimes you will find some industrial facility, they are using combined load. Some loads are related to single phase, some loads we are feeding by three phase. So there is load unbalance. There is unbalanced load in that case. So there is huge demand of this to mitigate this neutral current. Okay, neutral current compensation is also required. So we cannot feed these combined load using three phase 3 wire topology. Otherwise, neutral current compensation cannot be done using three phase 3 wire topology. So we require extra lag so that the neutral current can be compensated. Whatever the required load current can be, load neutral current can be feed by from the VSC. So three phase 4 wire, similarly as the single phase is categorized into single stage, two stage, battery-less, battery-based, and then battery without control, battery with bidirectional converter. So almost more than, how many topology we are having? More than 20 topologies are possible in these solar PV based microgrid system. You can go through the, these topology and you can simulate. So if you see the first conventional two-stage single-phase grid-tied PV inverter, what we are having? We are having a solar PV array. We are having this boost converter for MPPT purpose. Then we are having this VSC and directly grid. So we can feed the power. So now one point, if you are remember, in introduction, we have discussed the utilization factor. So what is the utilization factor of this VSC, this power converter? How much time we are using this PV inverter? There is no load. This is the grid tied PV inverter, and we are not having any kind of load there. So it is utilized hardly 5 to 6 hours in a day. In out of 24 hours, 7 to 8 hours hardly, because sun radiation is available hardly 7 to 8 hours. Rest of the time you have to switch off this inverter. So rest of the time this PV inverter is not utilized. So the utilization factor of this PV inverter is very poor. Very poor. 2/3 of the day. If the inverter used for SPV generation can be utilized as a voltage source connected during the night time. So what would be the solution? How we can reduce the cost through the payback, by improving the payback period. Payback period means we can utilize this converter for 24 hours. So during the loss of this PV array, we can operate this inverter as a power quality conditioner. In daytime, we can utilize this inverter as a PV inverter. When this solar PV array power is not sufficient, we can connect the load here, and this load can be fed from the grid, and this converter will work as a power quality conditioner. It will do all the function. Reactive power compensation, it will do the power quality, harmonic mitigation, load balancing, all three function, power factor corrections, all the function we can take from this PV array. We can take this PV array. So slowly we will improve the power factor of this particular system. The power converter involved, this will directly reduce the cost of operation if you are utilizing this converter 24 hours. So what is the solution? We can connect here, and remember toward the hardware side. So this is the the hardware components. Solar PV is also available. Boost converter is also available. These are the hardware devices, physical devices which are available. Few sensor we require to implement that with the load compensation. Few sensors are required extra, and we need modification toward the control. So this way we can utilize this VSC 24 hours. Earlier you were utilizing that VSC for hardly 7 to 8 hours, but now you are utilizing 24 hours. What is the mandatory condition with this two-stage grid-tied system? What is the mandatory condition? Grid must be there. Grid must be there. If grid is not there, we cannot operate it. We have to switch off this VSC. So the moment when there is islanding in the system, again VSC will be switched off. So again the utilization factor is still poor in this system. We have to take all the condition in mind. Grid is not there, PVR is not there. So how we will utilize this system? Again, we have to switch off. We don't have other solution. So we have came across this particular system. Even though we have not connected the battery here. And recently in December 2021, we have published this paper in Ideal Transaction on Industry Application. By incorporating the multi-mode features. And remember, this is very economic system. In daytime, still the utilization factor will be poor because we are not putting the battery. But suppose we are saying that we are utilizing this system in most of the time grid is available, and whenever we are having the islanding, we can use this system in standalone mode. So here we are having a PV array, and this VSC will do all the functions like MPPT, because boost converter is not utilized here. It is a single stage system, and here we can use some adaptive control. Some improved proportionate normalized least mean square based filter we have used for the current control, and for the islanded control we have used a voltage based control. This way we have recovered. I mean, whenever there is grid recovery, so we have decided the condition when grid recovers, we will give one signal. And if this control will get one, means this current control will be activated. Whenever there is grid failure, this control, this combination or this concept will get 0, and this islanded control will be activated. So in case of islanded control, we have to generate the voltage and frequency which will be matched with the load, because load always require, if it is a single phase system, 230 volt and 50 hertz. 230 volt and 50 hertz. So active power, if we have extra active power, it will be injected. After point of common coupling, at the point of common coupling, we are having the this VSC connected, we are having a load connected, we are having a RC filter, and grid is also connected through a combination of switches. So this is the novelty in this system. Static transfer switches we have connected, and these static transfer switches are supplied with the 1 and 0. 1 and 0 means on and off. On and off. And these switches are having the bidirectional power flow capability. Bidirectional power flow capability. How it would be bidirectional power flow means sometimes PVR is down, so we have to take power from the grid because we cannot interrupt the power across the load. Sometimes PVR is more as per the load required, so extra power can be injected to the utility grid. So the direction of power would be like this, and when PVR is down, the direction of power like this. When we are drawing power from the utility grid, first switch will be on and the diode of second switch will be on, so that we are having the perfect power flow like this. Perfect power flow like this switch, then this diode, and this power. When we are having the power flow from PV array to the VSC, the switch which is near to the PCC will be switch on. This switch will be on and the direction of current will be like this. And the diode of second switch, which is toward the utility side, will be on. So this is the flow of power toward the utility side. Why we are not going to switch on both the switches? Because there will be a huge losses. So we want to minimize, or we want to improve the efficiency. So only one switch and one diode we are going to switch on to get the bidirectional power flow. Isn't it? So this way we have static transfer switches here to connect and disconnect. And remember, whole the process is autonomous. We need not to switch mechanically anything. We need not to switch these STS, these means mod switching control, all those things. The mod switching control will take automatically whenever this synchronization controller, islanding controller will see that there is fault toward the grid side. So one again standard is there. I forget to mention one standard there. If you want to connect your system with the grid, voltage, frequency, and phase must be within the limit of IEEE 1547. IEEE 1547. If they are following these standards, if your system is following these standards, then only you can connect your PV array or your grid connected your Pbbs microgrid with the utility grid. But what is the disadvantage of this system? What is the disadvantage? Suppose if both the sources are disappear. Now PVR is not there and utility is also gone. Utility is also gone. Again, you have to switch off the system. So we have proposed a topology which is based on battery. Battery is connected with the bidirectional. So battery is interfaced through a bidirectional buck boost converter. The bidirectional power flow of power between the grid and the system is achieved through the solid state switches, static transfer switches. Rest of the thing is constant. We are having PV array. So two-stage system we are talking about here. Earlier we have talked about single stage. So both the system we have verified as single stage, two stage, as well as the battery without battery, with battery, battery directly connected at the DC bus. These are the DC bus line where your SPV array as well as battery are connected, and then we are having this voltage source converter. So again, voltage source converter is control in current control mode as well as in voltage control mode. So both the
One doubt,
yes,
sir, here.
yes.
Sir, can we operate the this system without using STS? Can we achieve the automatic power balance without using STS switch?
Yes, autonomous we can get, but in that particular system, your grid must be there. I mean, there is condition. Again, this STS switches has been implemented when you are operating your system or you want switching between current control and voltage control or between grid connected to standalone. You can see there are n number of systems which are there without switching. Grid connected is separate system, standalone is separate system. But switching from grid connected to islanding and islanded to grid connected has not been depicted yet. I mean, in solar inverter, they are having, you can find a number of application solar PV with MPPT controller running running the BLDC fan or a number of application is there. You are having a grid tied solar inverter in grid connected mode. You have a standalone solar inverter in standalone mode. But switching has not been possible without these STS, static transfer switches. So if you are not having these switches, your grid must be there. You can operate without grid. You can operate without grid. You can connect nonlinear load and you can activate permanently this voltage control. Or you are having this grid, but grid should be permanent. Otherwise, you have to shut down the system. Every operation is possible. I'm not saying this grid connected is not possible without STS. Operation will be possible, but switching of modes will not be possible. Standalone could be possible, grid connected could be possible and separately, but switching off mode without these STS will not be possible. You need some solid state switches or some kind of STS there so that you can have the switching from grid connected to islanding as well as seamless operation you want during the switching. So here we are having a design of two-stage single-phase photovoltaic battery energy storage based microgrid with buck boost converter controlled. Here boost inductor has been selected around 5 millihenry. Buck boost inductor is also selected. This DC bus capacitor 2500 microfarad filter resistance inductance. Then the battery parameter and the DC bus also selected 400 for 230 volt grid. Control of VSC without battery. So this is the control for this system. We don't have any battery. So how we'll control the DC bus? Simple, as you are going to control through your power quality conditioner unit, or you are going to control the grid connected system. So using a PI controller, you can put the PI controller and you can compare both the voltages. You can control the voltage. And the other control like power quality controller, how you will get, you have to sense the load current. You will multiply with the unit templates. Unit templates are nothing but these are the unit template synchronization signal which has been derived with the help of grid voltage. And there is adaptive filter to improve the response of this microgrid system. So we have used some adaptive technique here, and we have defined some steady state as well as dynamic responses of these filters, and we have derived this net active component of load. Net active component of load. Other side, from the PV array contribution, we have taken a MPPT technique, and from MPPT we have derived the actual power. And this actual power to derive the PV feed forward, we have taken care of this with the grid voltage. Grid should have the information that how much power is coming from the PV array. This way we have by all the contribution from the DC link requirement, active power requirement, and the PV array active power injection, and the grid load power requirement. Through all these three components, we have derived the net active component. This net active component is multiplied with the unit template to get the reference grid current. This reference grid current is compared with the sensed grid current to get the error. This error has been fed to the hysteresis controller to get the switching of this VSC in current control mode. And remember, in grid connected mode, we have well established voltage and frequency. The grid frequency and grid voltage is fixed now. So we have well established 230 volt and 50 hertz single phase grid. However, in case of islanded control, your load requirement is 230 volt 50 hertz. Your household load is required 230 volt and 50 hertz rigid supply. So what we have to do, we have to maintain from our control 230 volt and 50 hertz. So here you can see that through islanded control, we have to supply a waveform, a voltage waveform, which is having a 50 hertz and magnitude is 230 RMS. Okay, so this way we have using the 2 pi EF, we have initiated the theta, and for synchronization to minimize the error in theta, like load voltage theta and grid voltage theta, we have given this difference in PI controller to get the frequency, and this frequency is compared with the actual added with the the error frequency. So this way we'll get the actual grid frequency. So if there is a large variation in this frequency, constant frequency will be supplied to this control so that it can operate in islanded mode. Otherwise, this error will be very less and one signal will be supplied so that it can operate in grid connected mode. And then we are having this alpha. So these are the reference voltage. I mean, this is the reference voltage which we have generated. Sine omega t we have generated. VL star is nothing but VM sine omega t. So constant value we have to fed with this, and the actual load has been converted, I mean alpha beta to DQ. So we have got this VT and VQ. Other side we are having the sensed voltage. This is the reference voltage which we have generated. Other side we are having the sensed voltage. This sensed voltage is again converted into alpha beta to DQ, as is this is the single phase system. VTVQ we are having, and reference VTVQ we have compared. We have the sensed VTVQ and we have reference VTVQ to control this particular voltage, and given the error, voltage error is given to the PI controller again. So we'll get the DQ to alpha beta. And the output of these PI controller, we have considered the reference VSC current. This reference VSC current is compared with the actual VSC current to get the error. This error again given to the hysteresis controller to generate the switching in islanded mode. So 4 switches are there. 4 switches will be supplied by these switching sequence, and we are having a well established islanded operation whenever grid is not there. And this STS signal will decide, this synchronization controller will decide that which control will be activated at what time. Suppose grid is there, then your STS will get one signal, so current control will be activated. If STS is getting 0, your islanded control will be activated. This is the control for this particular unit. I mean, battery has been involved. So how we will go for the battery? How we will approach this battery in current control mode? So we have to take same as PV array. Same as PV array, we have to take the battery contribution. So we'll sense the battery parameters and it will be supplied to our control. Rest of the things are same as we have seen the control over there. Okay. How will estimate the different parameter? So VT we have estimated like we have converted into alpha beta actual signal and we will estimate the phase peak voltage. And then unit template has been estimated. RMS means the sensed voltage divided by VT. This phase peak voltage will get the unit template, and this is the active component. This is the equation which has been modeled in the MATLAB. And then we are having this PV feed forward, then net active component, reference current generation, then error which has been supplied to the hysteresis controller. Now the question is how you will control this DC bus, this bidirectional converter, because both the operation charging and discharging we have to take care through battery. So what we will do, one time it will operate as a buck converter and another time it will operate as a boost converter. So cascaded PI controller we have to use this purpose. Cascaded PI controller means the outer PI controller, it is nothing but it is a PI controller. Voltage controller is nothing but PI controller. So the outer PI controller will take care of this DC bus. So in simple grid connected system, we are having a DC bus with the VSC control. But in case of battery PV based system, this DC bus will be switched to the DC bus control will be switched to the bidirectional converter control. As we have to control the charging and discharging of the battery. So whenever it is more than the reference value, so battery will be charged. And when there is the reference value, DC bus voltage is less than the actual reference value, suppose 400 we have set. If it is a 398, so we have to supply power to the DC bus. It will be observed there is requirement of power at the DC bus. So what we will do, we will supply power to the DC bus. So under outage of PV source and utility, what we will observe? We will observe there is a requirement of power supplied at the DC bus so that we can feed the power to the load. So this converter will operate in boost mode and there is power flow from battery to the DC bus. When PV array power is available and grid outage is there, so there is increase in the DC bus and we can charge the battery in this way, in this fashion. I mean, this SOC and all those things are also involved. If SOC is less than we higher, it means SOC is more than 80%, then we will operate in FMPP mode. How we will get the mode switching or mode shifting control? So we will sense all the grid parameters, voltage, frequency, and theta. If these are within the limit, yes, we will have grid connection. If these are not in the limit, we are having the islanded mode. And accordingly, the STS signal will get 1 or 0. This is the flow chart for energy management in this Pbbs microgrid. So we will start and then we are having the monitoring of grid parameter. PG, if this grid power is 0, we will activate these STS, means we will supply 0 signal so that it can be shifted to the islanded mode. If PV array grid power is not 0, we are supplying or we are drawing the power from the grid. So we will operate in grid interactive mode. Power will be shared between grid, battery energy storage and load. Again, we will check is PV array sufficient to supply load and SOC. Okay, if it is greater than 0, then we will first priority will be we have to check the SOC of the battery. If no, We will also, if PVR is not there, then also check the SOC, because in that case, we can charge the battery from the utility grid. Otherwise, what we can do, we can feed the load and as well as we can charge. In a standalone mode, again, we will check the condition that PVR is greater than 0 or not. We will check the SOC, and in both the cases, either it is greater or 0. So B is charging till SOC max. Otherwise, what we will do, we will operate in off mode, because in a standalone, there is no way to flow the power. So either we can charge the battery or we can meet the load demand. So if load demand is also less, I mean 2 kilowatt power is required and SOC is also as per the limit. So rest 3 kilowatt we cannot feed anywhere. So what we will do, we'll operate this PVR in off MP mode. If SOC is not greater than SOC minimum, so what we will do, we will do the load shedding, because great PVR is not there and you have run your system for 7 to 8 hours. Still, you have not recovered the sources. So what you will do, you have to do the load shedding. Only emergency load you can switch on. Rest of the time you can off other loads which are not, very important. Simulation result, we have do the comparative analysis among the proposed technique which has been used for Allen detection and mode transition. So here we can observe we are having a grid recovery at 0.2 second and grid outage at 0.4 second. So this is the STS with the proposed control, and this is the STS static transfer switches on and off 1 and 0 through the conventional simple voltage control. So what we have observed, if there is fluctuation in the voltage, little fluctuation, here you can see from 1 per unit, it is, even though it is within the limit, IEEE 1547, it says, if it is fluctuated within the 0.88 to 1.1 per unit, your control should work fine. You can connect with the grid. But if you see the conventional system, still there is chattering when this voltage is dipped to the 0.88. So chattering in there means at that particular moment, this your ST is gone in off position. And when there is increase in the voltage, the STS, there is large dip or large off in that signal. However, this should be connected because this voltage is under permissible limit. It is not going beyond 1.1 per unit. So accordingly, you can get the interruption in the grid current. Okay, there is fluctuation in the load voltage also. So sometimes you may damage your load. However, if you are running your proposed control, you can see the signal. There is no any kind of interruption, even though your voltage is fluctuating from 1.2 to 0.88 per unit. So this is the advantage, the system which we have developed. So all other parameter we have also verified, like at 0.4 second, there is grid outage and power quality are maintained, like grid current is sinusoidal here, and the battery reaches to charging mode from the discharging mode. Suppose the SOC of the battery is not maintained after 0.4 second. So battery reaches slowly it is going to the charging mode. So negative current, we are considering that battery is in charging stage. Positive means battery is discharging. And in another figure, you can see that at 0.2 second grid is recovered. So both the grid voltage and load voltage both are well synchronized. And after that we are having current. So current is out of phase with this voltage, which means power is injected to the grid. Out of phase, perfectly out of phase means unity power factor operation we have maintained. And the load current is square in shape. However, grid current maintained sinusoidal. And other VDC is constant, V battery and other parameter, PV array parameter we have maintained constant. These are the harmonic analysis. I mean grid current TSD and load current TSD. So load current TSD is 31% around, and the grid current TSD we are getting 4.16, which is within the limit of IEEE 519. Response at steady state and outage of PV source. So steady state, we have already seen some steady state parameter, but at outage of PV source, VSC is carrying only harmonic power. VSC is carrying only harmonic power because active power from the PVR is not available. So what this VSC will do? This will compensate the harmonic. And you can see the grid current, how it has been reduced. Earlier it was carrying the active power. Now it is carrying the power which is required by the load only, which is required by the load. Earlier it was carrying load plus PV power. And there is phase reversal we have realized in the grid current, because now we are drawing the power after 0.3 second. Earlier we were injecting power to the grid. Now experimental validation. So we have experimental validated this particular system with DSpace 1103 and Ametek based solar emulator, this ExciteMate battery bank of 21 ampere hour, and then semicron based switches. So this is the experimental setup which we had developed at IIT Delhi laboratory. And here we are having a solar PV emulator, VSC, boost converter, interphasing inductor, battery storage, various sensor and optocoupler boards are there in this case. And these simple static simple static transfer switches, semicron based switches we have utilized for STS. And this is the MPPT performance. So here we can observe when the MPPT is around near to 100%, and it is achieving the 100% power at MPP. And these are the synchronization of Pbbs microgrid at recovery of utility. So at this grid voltage recovers, both the voltages, grid voltage and load voltage are synchronized. Immediately after one cycle, we got this grid current, which is out of phase with the grid voltage, and battery is in floating mode. And this is the desynchronization of PV battery based microgrid outage of utility grid. So outage of utility grid voltage is gone. However, load voltage is maintained. You have not, because islanded control immediately has come into the picture. Okay, immediately has come into the picture, so that the load voltage frequency has been maintained. These are the constant feeding mode. So here you can see in B figure, you can realize the negative sign shows that power is being fed to the grid with the near to close to, unity power factor. And the grid current TSD is 5%. However, load current TSD, you will find out that is 31.8%. And these are the some intermediate signals. So dynamic response of this particular control is very good. Dynamic performance at outage of both the sources. PV source is not there and then grid is not there. So in case of outage of PV source, there is reversal in the grid current, and the magnitude of grid current is also reduced because BSC, this PV array power is not available. PV array is not available, so only load is there. That amount of power will be drawn from the grid. Okay, and here you can see PV is also not there, and there is outage of grid also there. Outage of PV is always in 0. You can see the third waveform in third figure, and immediately the grid is also gone. So what will happen? Battery reaches to discharging mode. Battery reaches to discharging mode. Why battery reaches? Because load always, we have to fulfill the load demand. So battery from it was still in, it was already in discharging mode, but as grid and battery was contributing to the load, but as grid is not there, so battery will discharge more because grid power now is not available. And as PV array is recovered, so grid current is increased, and this VSC current is also increased, and however this power across the load is not disturbed. Now this was all about the single phase. Now we are having a 3-phase microgrid. Quickly we can go through it because the control and all those things are constant. So from the DC side we have same. However, toward the AC side, in all phases now we require STS in all 3 phases. So 3 signals we have to initiate from the control. So 3 PWM pins we require to give signals to these controls. Okay, and this topology has been published in Nitroid Transaction on Industrial Informatics in 2019. So this is the 3-phase design. You can go through it. These are the controls which are required. bidirectional control, converter control, VSC control, STS, and boost converter. So current control, again, 6 pulses we have to initiate using adaptive current control. However, in islanded control, similar, instead of taking alpha beta DQ, now we have to take ABC to alpha beta for this 3-phase voltages, and we will generate the reference voltage VD star and VQ star from reference generation from VT sine omega t, like that. Okay, here we can see that we have generated the reference load voltage VL star, VLB star, VLC star from sine omega t minus 120, sine omega t plus 120. Okay, and similar cascaded control has been utilized. Here we have used the enhanced phase lock loop for this synchronization and desynchronization controller. So if these parameters are within the limit, theta error, per unit voltage, and change in frequency, if these are within the limit, we are having a grid connection. If these are not within the limit, we don't have the grid connection. And this is the structure which has been, because in case of PLL, what is the demerit? We are having only one single loop, okay, for filtering as well as for initiating the synchronization angle. However, in case of enhanced phase lock loop, we have separate unit for frequency and phase. We have separate filtering unit for this fundamental voltage extraction. So this is the beauty of this EPLL, so that the dynamic response of this EPLL is good as compared to PLL. Here you can observe chattering and dynamic response in case of change of frequency variation in case of PLL is more as compared to EPLL. And here you can also see the phase differences between these two thetas. Okay, you can see, observe these theta which has been so simulation performance at outage of grid at 0.4 second. The grid voltage is not there. However, the load voltage is maintained sinusoidal throughout the process. The VSC current is VSC current are reduced. VSC currents are reduced so that you are getting only load power. Here the synchronization at 0.6. So grid current we have received, and both grid voltage and both grid voltage and load voltage are well synchronized, and VSC now compensating the load. Okay, this is the performance under dynamic condition like load unbalancing we are having. So under load unbalancing, one phase is removed. However, grid current are maintained. Grid currents are maintained sinusoidal in nature. Okay, here TSD of grid current is 4.5%. Our TSD of this load current we have 26.91. Okay, and these are the comparative performance under PV feed forward loop. So here 0.3 second we can observe grid current is balanced immediately, means we are getting the grid current. However, this grid current is oscillating and they are reaching a steady state after 0.34 second. Okay, so this is the advantage of having PV feed forward, and if you are not having, so what would be the disadvantage of that particular system? Experimentally, we have also verified this 3-phase system also under outage of seamless transition of microgrid, and then seamless transition as restoration of the grid. And this grid distortion you can see. So under grid distortion, the grid voltage TSD is 11.31%, and the TSD of load current is 22.80 power quality indices. However, once we switched on this converter, voltage source converter, we have found out that TSD of grid voltage as well as grid current is within the limit of IEEE 519. It should be less than 5%. So we are getting 3.52 and 3.99 in grid voltage and grid current. However, the power injected is around 2 kilowatt, 1.97 kilowatt power has been injected to the grid. So these are the dynamic behavior at outage and recovery of PV array. So you clearly you can see the phase reversal of grid current. Here we were drawing power from the grid, and immediately as PV array recovered, it is reaching to MPP. This is the time where it is taking to reach the MPP point. So as the MPP reached, immediately there is phase reversal, and the steady state we are getting here after recovery of PV array. So under zero PV insulation, battery is more discharged because we have to feed the power to the load. So battery is discharged in that particular. And this is the 4-wire topology which we have implemented. So here I'm going to stop. I'm not going to discuss, otherwise it will take another 1 hour to discuss all these topology, and we are having also some other topology. So here we are going to conclusion. A detailed investigation of grid interactive PV system has been carried out. We have addressed all the power quality indices, and then the TSD as well as seamless transition we have observed under grid restoration and grid outage conditions. These are the few references which you can follow. And thank you very much for listening me, because this lecture after lunch is very difficult to sustain, I mean to listen. And this is my contact information. If you are, I mean, if you want to discuss anything, you can. So any question from the participants?
Participants, if you have any query, you can ask directly to sir.
Hello, sir.
Yes,
Yes.
Karthik.
Hello.
Yeah.
Yes, sir. I'm
Please.
Karthik, sir. This is the third session I have attended yours third time, sir. In the last month when you given lecture in NIT Manipur on the same Atal platform.
Okay. So both the things we have discussed there also. Yeah.
Actually speaking,
That's
after
great.
seeing your name in the schedule, I thought of registering for this FDP, sir. So because I learned a lot of things in those two sessions.
Thank you so much. Yeah. So
I have
at least
queries,
now
sir.
I think you should start simulating this topology now. I hope
yes, sir.
got enough information. You should go for the simulation as well as, I mean, if the possible, then you can publish some papers on these topology. Yes. Yeah, please go ahead.
From the last month, I have already implemented some simulations, sir. So where I'm getting a lot of doubts. But I may not ask all the doubts here.
Yeah, means we cannot discuss all the doubts here, but few we can take. Couple of query we can take, and then you can mail me if there is further discussion. Then you can mail me. Yeah, please go ahead.
Yeah, sir. One is when we select the PV parameters in the simulation. So like a single stage or two stage. So we have to select the PV voltage MPP equal to 700 volt or OCC equal to 700, sir. Which one should be equal to 700 volt?
VOC we have to select 700.
VOC if it is a single stage, for example.
No. If it is a two stage. If it is a single stage, then it should be higher. I mean 750 or 800 volt you have to select. As I discussed, in case of single stage, there is no decoupling unit. So we have to go for higher unit. Number of series, 1 or 2 panel you can increase in series. There is series panel, parallel modules. So series and parallel modules. So in series, instead of taking, suppose for for two-stage system, you are taking 23 panel for 400 volt or for 700 volt. You can take 25 panels for single stage system.
Sir, sir, one more query, sir. Suppose when we consider the three-phase system with PV and along with some sort of nonlinear load, so then what are the things we can analyze, sir? Like unbalanced. One is the unbalancing condition we can go, and
yeah. So I mean there are, if you are going a three-phase system with the grid connection along with load. So you have
without battery.
Yes,
sir,
without battery. So always, I mean, steady state operation, everyone, I mean, if you see the steady state may be fine, but everyone will ask for the dynamic condition. So dynamic you have to verify. So what would be the dynamic condition in three-phase grid connected PV systems? You can go for insulation change. You can have 500 watt per meter square. You can change the insulation from 500 watt per meter square to 1000 watt per meter square. Second one, you can go for the load unbalancing. Okay. Under load unbalancing, what will happen? Load power is reduced. So more power has to be injected to the grid. Okay. Because suppose you have investigated or you have developed a 5 kilowatt system, PV array, 2.5 kilowatt. So 2 kilowatt load you have designed. And further, if one phase load is removed, so this load may decrease to 1.5 or 1 kilowatt. So extra 0.5 kilowatt or 1 kilowatt, it should be injected to the grid. So grid current immediately will increase. So these two conditions must be verified. Third condition, maybe you can verify for grid voltage distortion. Okay, interruption in the grid voltage or some other condition you can also verify. But these two conditions are mandatory whenever you are going for a grid connected PV system. Means n number of ways to verify these topology. But these two dynamics you must mention.
Sir.
Yes.
Yes, any other query?
For the one more query, sir, from my
Yeah,
side
yeah.
only.
Yeah, please.
Sir, for
Please
the
go ahead.
same set system, when we consider experimental, so how can we approach to inject the power to the grid, sir? I mean, because in the papers I'm going, D-space, everyone is using D-space controller and inverter, semicron, and the
Yes.
PV, everything
Yes.
is. So how
Yes.
can we achieve the injection of power into the grid? What are the things
Yes.
required?
Yes. So nothing extra. I mean, it is not required anything because your power limit is within the grid infrastructure requirement. Suppose, I mean, your grid infrastructure has to be changed when you are having more power fed as compared to the power which has been drawn. Suppose you have designed a grid infrastructure for, I mean, 1 megawatt plant you have designed, and 1 megawatt power has been drawn in a particular city, or 100 kilowatt power, you can take the example, can be drawn. But from the 100 kilowatt grid infrastructure, you cannot inject 200 kilowatt power because your transmission lines, your transformer, your relays, all the things are designed for 100 kilowatt, not for 200 kilowatt. So if you are having a power plant of solar power plant of 200 kilowatt, you have to design, you have to change your grid infrastructure. Okay, otherwise you are not able to, sometimes your transformer or some relays may be tripped, or you may damage the transformer also. So in laboratory, if you are having a 2 to 3 kilowatt system, you need not to change anything. Just simply you can connect the auto transformer, and you are having a converter output through interphasing inductor. You can connect to the grid directly. Okay, and you have to monitor that, because I mean, you have to watch carefully that your power factor. What is your power factor? First thing is the current and voltage. What are the phase difference between current and voltage? Okay, it is out of phase or it is in phase. If it is in phase, so you have to measure the current and voltage very carefully. So if you are measuring correctly, whenever power injection from PV to the grid, there is negative power, or the current will be out of phase from the grid voltage. If you are drawing power, the grid voltage and the grid current will be in phase. So using these measurements, using these scenario, I mean, grid voltage and grid currents, you can identify either we are going for injection of power or we are drawing power from the utility grid.
Sir, one last query, sir.
Yeah, please go ahead.
Sir, during the simulation, what I observed, when I consider three-phase grid, and when I started measuring THD of nonlinear load and grid side, what values we have to consider for grid impedance, sir, R and L value, because it is showing some impact on THD value. What I observed.
Immediately you can go this X by R ratio. Okay, it should not. It should be between X by R ratio must be between 7 to 15, not more than that, or not less than that. So V grid and this condition we are not considering here. Okay, we are going for the ideal grid. So R value you can select, if I am not wrong, 0.01, and 0.4 millihenry you can consider the inductor value. So you will get the ideal grid, and you will be having a good THD in grid voltage. If intensely you are creating the disturbance toward the grid side, so you have to increase the inductor value.
Okay, sir. Thank you, sir. Thank you so much for answering my queries with patience.
Thank you. Thank you.
So definitely, I will be in touch with you, sir. For
Yeah,
more on the
sure.
things,
If you are
thank
facing then any issue, you can mail me. I'll reply it. If I'm not replying,
thanks.
again mail me. I'll try to reply. Yeah. Because it is difficult to finding sometimes time to answer all the queries, or sometimes mail all the reply all the mails.
Okay, sure.
Yeah.
Thank you, sir. Thank you so much.
Any query from other participants?
Sir,
Yes, please.
I'm audible.
Yeah, Puneet.
Yes, you are audible.
Ji, sir, there are two concepts. One you have discussed about your this boost converter, and one is buck boost converter.
Yes.
Okay, in that cases, if we go to the on-grid solar water heating system, under that condition, I think so buck boost converter is more favorable than boost converter.
Yeah, depending on the application, because here we are using for grid connection systems. So your solar water heating system maybe standalone, means it is a standalone system, not maybe. So in that case, if you have put some DC loads along with it, and this we require, sometimes we require less voltage and sometimes we require higher voltage. So this buck boost converter will be favorable candidate for that heating system, because voltage variation, depending on the voltage variation, because you are putting the number of number of panel you are putting in series and parallel, and your number of panels in series if higher according to your heating load or your heating requirement, so you have to buck the voltage. I mean, your PV average voltage is higher, and you have put the, suppose we can take the example of battery. PV array voltage is 100 volt and battery voltage is 48. So we have to utilize the buck converter. We cannot charge the battery from battery. So matching of these voltages must be there. That's why I have discussed this particular with the VSC also, how we can have the 700 DC link with the 415 volt DC link. Otherwise, there is desynchronization in the system, or desynchronization will take place, and you may have the disconnection from the grid with the VSC. So it will depend what kind of heating load you have connected or heating element, what is the voltage. If this voltage is less than the PV array voltage or PV panel voltage, obviously you have to go for the buck converter. If this voltage is higher than the PV, then you can go for the boost converter. So this buck boost will be the favorable candidate for heating loads.
ठीक है sir. ठीक है. Thank you.
Thank you. Thank you. Thank you so much.
Any other query? I hope so. Participants have enjoyed the session, and most of the queries are answered very satisfactorily. Personally, I was listening first time to Dr. Sailendra Kumar, and I learned a lot from this session.
It is great, and it is a pleasure to,
sir.
I mean,
it was very wonderful session, sir. It was very much informative. The people who are working in this area, definitely they are going from here something new. They have learned from here, and it is going to be helpful in their academic domain as well as in research. Now I would request Professor Shah to give the farewell remarks to the Dr. Sailendra Kumar.
Thank you, Dr. Asutosh Giri. On behalf of the Government Engineering College Bharuch and STTP Organizing Committee, I am very much thankful to Dr. Sailendra Kumar for this wonderful session. Let me briefly summarize this session. Dr. Sailendra Kumar has spoken about this multi-mode system. He spoke about the single phase versus double stage difference for this PV-based system, and the trade-offs between them, advantage, disadvantage compared, and then he spoke about the classification of single phase, three phase, this grid PV system with and without batteries, and then starting from the single phase BES PV based system for standalone as well as island combined system. He has spoken about different topologies. Then for 3-phase and 3-phase 4-wire also he has shown few of his research papers related topologies and experimental results, analysis, setups. So we are very much thankful to Dr. Shailendra Kumar for this wonderful session. Thank you very much, sir.
Thank you, sir. Thank you for this remark, Prashantji, and thank you. I would like to thank Bharuch, as this GC Bharuch, as well as Astos ji for inviting me and giving the opportunity to present my work as well as discuss with the participant. I would like to also thank to the participant, those who have listened me, because this is very hard time after lunch. It is very hard to I mean, focus on that particular, studying or to focus on these lectures. Yeah, thank you so much. Thank you for the
And
opportunity.
one more information I would like to pass on to our participants. Me and Dr. Shailendra Kumar sir is editing one book also together.
Yeah.
And
Yes,
hopefully that book will be available by the month of June this year.
yes. Yeah.
And you people can enjoy reading that book also.
Thank you, Astos ji, for this opportunity.
Thank you very
Yes,
much,
yes,
sir.
yes,
I am very much
yeah.
obliged for your presence here.
Yeah.
Thank you very much.
Thank you, sir.
You have
Thank you so
given
much.
your time, valuable time to our participants. It is quite wonderful session. Thank you very much for this.
Thank you. Thank you, sir.
Thank you.
Thank you, sir.
Now, participants, we will meet again at 3:45 after very nice tea. You just take within 15-20 minutes. And we will meet again at 3:45. Today, the session will be taken by, the third session will be taken by Dr. Sanjay R. Joshi, Principal of the Government Engineering College, Bharuch. And that session will start sharply at 3:45. So please stay with us, have a cup of tea, and then join again at 3:45. Thank you, participants, for making the session interactive. Thank you very much.
Sir, Astos sir, can we have the current session slides?
Yeah. He will provide us. As soon as it is available, I will immediately send into the group.
Okay, sir. Thank you.
Okay.